Good afternoon, scholars. Welcome after the lunch. I hope that you have been learning a lot during these 3 days, and this being the last session, we have a very special invitee who is here among us today. Professor Jagadeesh Kumar, sir, Emeritus Professor, Department of Electrical Engineering from IIT Madras. Sir actually started his journey of education here, a student of College of Engineering, Guindy, where he completed his BE Electronics and Communication. He moved to IIT Madras for his MTech and also his PhD in Electrical Engineering. So, sir has joined the Indian Institute of Technology, Madras, in 1984 as a senior scientific officer, after which in 87 he became a lecturer, 1990 assistant professor, 95 associate, and in 2000 he became a full-fledged professor. Sir has also been a visiting faculty and related to teaching and research at SERD Bangkok, Thailand, also in various other universities in Deutschland, also in King's College, London, UK, related to research. So he is also the proud recipient of the DAD Fellowship, and he is going to speak to us today on the topic Research Planning and Development. He calls it a researcher's odyssey. I saw the first slide. So odyssey is a very huge journey or a voyage that is full of adventures. I'm very glad that Sir has accepted our invitation to be here and speak about his research experiences, which is going to be hugely beneficial for all of us. So before inviting Sir for his lecture, I invite my director, Professor Dr. C. Umarani Madam, to felicitate our resource person for the day. Sir, please accept this token of our love and appreciation for you. Welcome to Center for Research, Anna University. Welcome to the Induction program. Thank you, sir. Over to you, sir. We will have the session till 3:15. Yes, sir, it works. 3:15 and then a short Q&A session also. Thank you, sir.
So, good afternoon. As a teacher, the session I really hate to teach is the session just after lunch, right? There is a proverb in Tamil, "Unda mayakam tondanukkum undu." Right? I know all of you have lunch, and I hope the lunch has been good, but I will try to keep you awake. Okay? I am really glad that for whatever reason you have chosen to do research. If you look at a country, right? A country is rich or poor is not decided by how big the country is, what are the resources available in the country, right? And nothing else matters. What matters is the people inside the country. One example is Japan. Japan has literally nothing, right? We have aluminum in excess in terms of ore, iron in excess, right? To some extent, 20-30% of our oil needs come from the northeast, and of course we have some in the southern basin and Bombay High, right, on the seas. But if you look at Japan, they have nothing. They have no iron ore or any kind of strength in them. But if you look at it, they are still the second richest nation in the world, right? And again, you look at Norway, most Scandinavian countries, the difference is the people, right? For a long time, majority of Indians were illiterate. I don't know how many of you know. When we got independent in 1947, only 12 out of 100 people could read or write, right? and that also in their native language. And if you look at people who could read or write English, it was only 3 out of 100, right? So today, of course, we have come a long way up. We have our literacy rate climbing up, and in our state, it is more than about 90%, but we still lack the 100% that many of the developed nations have. The second that determines a country's advancement is the number of educational institutions, higher educational institutions that it possesses, right? Almost starting from my career at IIT Madras, I have been going to Germany quite often. Almost every alternate years I used to spend there. I have very good collaboration with the German group there. The one thing that struck me, a lot of things struck me at the time. The one thing that was academic, the first time I went to Germany, you should remember this was 1986, and I don't have a photograph on my. Our airport was literally nothing, right? From there you land up in Frankfurt, you just think that you have gone into utopia, right? And their roads, everything was, the best thing is you stand on the road, you have so many different cars. In 86, IIT Madras had only 2 professors owning cars, right? And to cut the story short, the one thing that I really liked about Germany was you can take the map of Germany, close your eyes, put your finger anywhere in Germany, walk in any direction, right? Within 40 kilometers, you will come across a very big university. I mean, university that is admitting 40,000 students, right? We don't have such universities even today. IITs, the first 5 IITs have started admitting 10,000 students, and that's it, right? And of course, once you have the manpower, you will also have the industry, you have everything that goes along with that, right? So, really what we need, people say, oh, what so many PhDs, what they are going to do, right? The same argument was given when the government wanted to expand engineering education, asking private people to come. They said, what are we going to do with so many engineers? We don't have so many industries. But today, Tamil Nadu alone produces about 120,000 engineers, and most of them find jobs, right? Maybe they don't get jobs they are trained for, but that's not the problem at all, because once we start growing, we will establish a kind of ecosystem which will have people doing what they want to do and also getting a nice life that they like. Okay, so let me start with my presentation. So this is a presentation, I don't know, I've been giving for almost 10 years now to at least the research scholars who join my department. So some of the initial slides are common to everyone, but later I have no choice. Being an electrical engineer, the examples are all electrical engineering examples. So bear with me. Don't worry if you don't understand exactly what is the topic, but you understand the basic idea behind the topic. That would be more than adequate from my point of view if you take that along with you, right? Now, the first thing is, of course, I have to give credits to my students. My first PhD student, he recently retired as director of National Institute of Ocean Technology. So I'm too old. And of course, Aparna is the most recent student. I still have to graduate 2 more students before I say I quit. Okay. So let's look what is R&D, right? I mean, everybody says, okay, research, right? Generally, it's advancement of knowledge, science, and technology, but different people say different things, right? For example, Redman and Mori, that's a nice book. I don't know whether it's there in the library. It's available in the IIT library. Research, a practical step-by-step instruction or something like that. I don't exactly remember the title. They say research is systematic effort to gain new knowledge, right? On the other hand, you take the book from Clifford Woody. It says you define, redefine problems. You say collect, organize data, then make deductions and reach conclusions. Test the conclusions and determine they are correct or not, right? So he puts so many, but it doesn't matter. Research, as we all know, is something finding new, right? When it all started, research was always groundbreaking research, right? Somebody found gravity, right? Newton. Why Newton found gravity? That's a groundbreaking research. But today, if you look at it, maybe all over the world, 100,000 PhD degrees are awarded. And if you look at all this, they are not really groundbreaking research. Hardly few, 3 or 4 are groundbreaking research. Most of them actually advance the knowledge in their chosen area, what I would mathematically say delta x, right? So we already have x, you will have to put delta x. So I am sure delta x, right? Those of you who have learned perturbation theory will really know that it's not that difficult, right? Delta x is just a perturbation, right? So it should be possible to do research and get that delta x, okay? Of course, this is something, why do you have to do research, right? These are the various reasons that you can look for research, right? In fact, way back in 1980, when I wanted to do PhD, believe me, the only reason why I did research was I wanted someone to call me Dr. Jagadeesh Kumar, right? Because after school, I really wanted to become a doctor. But you know, what we want to do and what we end up doing, many times don't happen that way, right? Very few people are very lucky to do what they want to do, right? So for various reasons, I just could not go into medical, get a medical education. Of course, I do that now. I work in biomedical engineering, and sometimes I used to boast I know in certain areas of medical engineering more than the doctors, right? So that's my reason to do research. I wanted to get the prefix doctor. But it doesn't matter what is your desire is, doing research for any of these reasons is not a problem, right? Okay, even if you think that, okay, if I have a PhD, I will get a government job, fine, right? No big issue. Okay. Now, once you have, all of you have decided to do research, how to start, right? Anything you want to do, starting is always a problem, right? Where to start, when to start, okay? There are several ways of doing that. If you have an idea, right, then of course it's easy. For example, again, I am really sorry I can give only examples on electrical engineering. Improve storage battery performance. Today, you know, right, all the cars are becoming electric cars, and one of the problem with electric cars as it stands today is the battery, right? Everything else has been solved, right? The drive is really nice now, which was not so true 5-6 years ago, right? The only problem with electric vehicle is battery, right? So if then you look at that problem and you have an idea, okay, I can do something to improve the battery performance, or I can invent a new battery, right? Then you can start doing research in that area, right? Okay, that's a start. Or experience. I mean, all of us have experience, right? I think yesterday evening I was here conducting a faculty interview. The first thing that I saw, big difference, we are just opposite each other. I don't know how many of you know, IIT Madras is on the other side of the road, right? But for my surprise, the mosquito in the campus is quite high, right? It's not so bad in IIT Madras. I don't know what IIT Madras is doing to control. I will find out. So they said, okay, I am bugged by this mosquito menace. I will find a solution, right? That's one way of starting research. But the most easiest way is the last one. That's why I put it in red. Easiest method is just read research articles, right? Once again, I go back 43 years ago, 1980, I applied to do PhD at IIT Madras. I got selected. I mean, IIT Madras has a slightly different system. Selection is based on commonly on everybody, and you can choose the guide. You can choose your area, you can choose the guide. Even today it's something like that, but compartmentalized, right? Because now the department has grown very big. So anyway, again we are deviating from that. So I got selected, I had to select a guide. So I went to Professor Shankaran and asked him what I can do, and he explained to me what is research and how to go about doing it. And he said, if you are interested, this is my area, you can join me, right? Then of course I met others. Finally I decided two people, Professor Raina or Professor Shankaran. Then I thought, okay, I'll go with Professor Shankaran because he seemed to be very, what do you call, there is always another aspect of liking or not liking people, right? You take one look at them, okay? So he looked very friendly, and later only I knew that he is known as a very tough teacher, right? A perfectionist. If I had known earlier, I would not have gone to him, but he trained me a lot. I owe him what I have achieved today. So when I wrote his name, gave it to him, went there and said, okay, you take these courses. In 1980, I had to take only 3 courses, right? Not more. So then I said, sir, what is the research problem I'll be working on? He said, you have to select. Why are you asking me? And I said, it's guide's job to give the research problem. He said, no. If I give you a problem, you don't like it, you won't work on it. So you choose the problem, right? And I said, I don't know anything. How do I choose a research problem? You are asking me, you are experienced, you have already guided several students. He said, no, student must choose a problem. But I'll help you, right? And he said, go to library. There's no Google, nothing, right? You have to always look at books and books, right? And what area of your interest, you start reading articles. And if you understand an article, that means you have an interest there. Then you come to me, right? So I went to the library, started with IEEE transactions, 1980, 79, 78, and please remember each book has at least 30, 40 articles, right? So 1 year is 12 into 30, right? 360 articles, and 3 years is almost 1,000 articles. Nothing made head or tail to me, right? I could not understand anything. All Greek and Latin, right? Even though it's electrical engineering. So I was afraid to go back to Professor Shankaran. We have some faculty members, I am sure here also, are very well known to be geniuses. So Professor V.G.K. Murthy, everybody will go to him if they have a problem. So I thought I'll consult him, right? Instead of going to Professor Shankaran, I went to Professor V.G.K. Murthy. I was standing outside his room because there was another professor, Professor Radhakrishna Rao, another genius at IIT Madras. They were chatting, sitting and chatting. And I was just outside the gate and saw to it that neither Radhakrishna Rao nor Professor Murthy can see me, right? Because I didn't want to disturb them. I thought when Professor Radhakrishna goes away, I'll go in, right? Then obviously if you're close, you can hear what they are talking about, right? So they were generally talking about the situation at IIT Madras, some politics. Then suddenly I had this sentence. Professor V.G.K. Murthy said, Rao Garu, I mean, that's how he will address Professor Radhakrishna Rao. Of late, half the papers in IEEE transactions, I am not able to understand. Believe me, that really struck me hard. If Professor Murthy cannot understand half the papers in IEEE transactions, okay, 1,000 is not my limit. I should go more, right? So I went back and finally found one article by one Professor M. Sharman, 1:1000 inductive voltage divider, which I could understand. I understood exactly what he has done, what is the novelty about it, and so I came back to Professor Shankaran, gave him the article, and said, I can explain this to you, right? Then Professor Shankaran said, go and replicate what he has done, right? I really got annoyed at that time. I mean, I want to do research, and because by this time 6 months are over, right? And IIT Madras, you have a yearly progress this thing. So you have to be prepared to say what you have done. You cannot go to the progress review committee and say, oh, I did read 1,000 articles, but I did not understand any one of them, right? That doesn't look nice. Something you should have done, right? So reluctantly, I went and started doing the experiment in the lab. I arranged everything as was in the paper, switched on the power, nothing worked, right? And I tried my level best. I thought maybe I made this mistake, that mistake. Then finally, I wrote a letter to Professor M. Sharman, right? And about 25 days later, I got a letter from University of Stuttgart, where he was working. You have sent a letter to Professor M. Sharman. We want to tell you that Professor M. Sharman is no longer alive. He passed away on such and such date. I thought, okay, done. I cannot go on like this. So by the time I almost half or even more than half, I decided I'll quit PhD. This is not my cup of tea. Then, of course, again, if you are in that kind of situation, you need help, right? I went to Professor Radhakrishna Rao, then explained to him. So he was so nice, he came to my laboratory, looked at it, and told me exactly what is the problem. I fixed it, everything started working, and I went to Professor Shankaran. I said, sir, everything is working, come and see, right? So he came, appreciated, he said, okay, now we'll sit together and we'll discuss about the problem. So we chose a problem. I started working again for another 6 months. By this time, 18 months are over. I really have nothing to show for 18 months, right? And as I told you, I decided that I will quit PhD. So I plan to do that. So I think 1 year after I joined PhD, I started applying. I got a nice job in ISRO, Trivandrum. And one fine morning, I went to Professor Shankaran and said, "Sir, goodbye. I am not doing PhD. I am going away." Right? Professor Shankaran was really upset. He said, "Why? You are doing very well. Why are you?" "No, I am not doing very well. 18 months, I have nothing to show." Right? This will happen to you in your PhD career, because PhD is 99% hard work, 1% luck. Right? That 1% luck you must get somewhere in your progress. Right? And then he said, better talk to Professor V.G.K. Murthy, get his advice. So I went to Professor V.G.K. Murthy, and he said, "Okay, you give a presentation as what you have done." So that evening itself, I gave a presentation. Professor Murthy, Professor Bapeshwara, Professor Shankaran, Professor Ishwaran, 4 of them were there. And at the end, everybody said, "Hey, you are doing fine. Why do you want to quit?" I said, "What do you mean I am doing fine? I have no results to show." He said, No, you continue for some more time. Don't quit now." Right? And then Professor V.G.K. Murthy said, "I will talk to ISRO. I will ask them to delay your joining date." Right? So I don't know what he did. ISRO wrote to me saying that you are given 6 more months extension to join. Right? So by the time, you understand, I really lost hope. But 6 months, you can't sit idle, right? Sitting idle is something that I don't think any of us can do that. Right? You have to do something or other. So I said, okay, I will spend most of my time in trying to address this. And believe me, starting from that day I started working, 3 months down the line, I got my first IEEE transactions in magnetics paper, right? Then I immediately wrote a letter to ISRO saying that I'm not joining. And I was so reckless. I got a reply from ISRO. "This is with respect to your unsigned letter informing us that not joining. Please send the letter signed." Right? So I was in such a mood that I did not even sign the letter. I typed it, sent it. Right? So why I'm telling you all this is quite a few of you will go through this. Right? The first thing is, it is your PhD. Do not blame your guide. Right? You have to take the responsibility in your hands. Of course, your guide can help. If your guide cannot help, there are other faculty members. If you go to them, talk to them, they will help. Okay? That's very, very important. Okay? So, the most important thing is literature search. Right? This is very, very important because people all over the world are working in research. Right? Somebody could have done what you are thinking, that it's something new, but yours is not new. Somebody has done, right? This happens in history a lot, right? Okay. Then, when you read an article of your choice, there will be references. Go through the references, and the important ones you read again, right? So it's actually like a blockchain. You go through reference, that reference you go through, that reference you go through. And once you, the moment you read, as I said, I read 1,000 articles without understanding. Believe me, I read 1,000 articles, right? And not fully, right? I'll go through the abstract, I'll go through the introduction, I will go through what they are saying, and that's where I will stop, right? Because if you don't understand the introduction and what they have written inside, there is no point in reading conclusion, references, nothing, right? But once you understand a paper, Then you start looking at the references and go through them, right? That's very important. Then find, are there any gaps, right? I'll talk about it with examples later, how to find gaps, right? And at this point of time, you must define the objectives of the research. This objective may not be the final objective in your thesis, but it's very, very important that this should happen anywhere between 12 months to 18 months. If you are there, then you have crossed halfway through your PhD, right? The moment you know what are all the objectives of your research, half your PhD is done. Believe me, right? So now I put this chosen area. Again, if you want, you can redefine, do a literature survey, formulate specific objectives. The next is, of course, if your work involves experiments, then you should look for apparatus materials to do the experiments, design and conduct experiments, get the work evaluated by peers, that is conference and journal papers. Now, every university says that you must have 2 journal papers to submit your PhD thesis, so which is another area that you should become expert at. Then, of course, write the thesis. Now, there are different types of R&D. There is something called the fundamental research. I put fruit juice results. I'll tell you what it is a little later. Then applied research, right? There is nothing wrong in choosing any one of them. Fundamental is a little more difficult today than applied research. Applied research is, right? So, as I said, once you do a research, your aim is to write conference and journal papers and get them published, right? Which means you should have done something new, you should have improved something, right? That's very, very important, right? You have come up with something new. Okay, this is again from Professor Shankaran. When I met him first, this is what exactly he told me. I put it in slides, right? You take a cup of orange juice, right? And you measure color, viscosity, acidity, sugar level, whatever you can measure, right? I put only something that came to my mind. Expose it to sun for 1 hour, 2 hours, and 3 hours. At the end of each hour, measure all these parameters again. Believe me, you can write a paper on effect of sun rays on orange juice. Nobody has done it so far, right? Now, the nice thing about it is, you can take grape juice, repeat the same, then write the second paper, effect of sun rays on grape juice. So, I have put it very crudely here, but most of the time when you do research, you start somewhere and expand, right? And of course, I removed the other slide, one slide, next slide I always put. After you have exhausted everything, right? Apple juice, pomegranate juice, right? You can write a review paper, effect of sun rays on fruit juices, right? Combine everything and write one paper, right? Okay. From this point onwards, I am going to give you examples from my own career. So it will be more or less electrical engineering based. But as I said, don't look at the problem, look at the idea behind the problem, right? You need facilities, but believe me, most researchers doing research, you don't need such high funda facilities. If you have high funda facilities, well and good, right? Even otherwise, you can do a lot of work, find something new with very minimal facilities, right? Yeah, I am going to give some case studies, something really old, and then my own examples. Okay, this is a simple thing. Even today, it's possible, but really, really very difficult. Mix two chemicals and report the reaction, right? I mean, this got a Nobel Prize in 1945. Okay, you know whom I am talking about? Sir Alexander Fleming. By the way, how many of you know what Alexander Fleming did? He was a soldier, right? He was a soldier in Scottish regiment, and he was stationed in London. And he joined a rifle club, right, called St. Mary's Rifle Club, which was part of St. Mary's Hospital, right? And he's a very good marksman, okay? So after his discharge from the army, the St. Mary's Hospital wanted to retain him, right? Because he was a very good marksman, okay? So they told him, I mean, just join us, you can do something. So Alexander Fleming said, okay, I will do research, right? So he did research only to be a member of a rifle club, right? I mean, you cannot find anything funnier than that, okay? But of course, he did a very good job, okay? But many do not know that he published his first work on penicillin in 1928. But the actual penicillin was done by Howard Florey and Ernest Chain in 1940, right? This will happen. You publish a paper, nobody reads, I mean, no citation, nothing, and suddenly you will see that it is really groundbreaking, right? This is one such paper, 12 years, nothing happened, right? And suddenly, Howard and Ernst, they were doctors in the army, so they wanted a chemical to treat wounds, right? They found Fleming's paper, they contacted him, then they actually made a process of penicillin, because what the method of making penicillin invented by Fleming is very crude, and you cannot do a lot of them, right? So the actual method was, all three of them got, I mean, even though we say penicillin, Alexander Fleming, all three of them got Nobel Prize. Other two are not talked about at all, unfortunately. So they did that. And the another glaring thing is, the first patient to whom the penicillin was given died, right? Died very quickly, right? Because people did not know the allergy to chemicals, right? So drug allergy, okay? So if you, of course today we don't use penicillin, we have much better antibiotics. So if you are going to be administered penicillin, I don't know how many of you, I don't think any of you would remember. In my younger years, if the doctor has to give a penicillin, he will first give a test sort, wait for 1 hour. If there is no reaction, then only he will give a penicillin injection, right? Okay. Again, mix two liquids, report the reaction. This again got a big award called Lasker Award, Alexander Wiener. Anybody knows what he did? He invented the blood group, but for that he did not get the prize. He also found that every blood group, A, B, O, right? A, B, A, B, O has something called RH factor, right? The RH factor came because he used rhesus monkey serum, but today we know it's a protein, absence or presence of protein. But that saved a lot of lives, right? Again, if you looked at it, you just put two on a petri dish, see whether it reacts or not reacts, right? Not a great research, right? Okay, and of course, Landsteiner is again not talked about. The actual work done was by Dr. Landsteiner, Alexander Wiener's student, right? Okay. These two are really very popular one. This is not so popular. So when I wanted to do PhD, the topic I chose was ferromagnetic materials, right? So these are the ones. The problem is that if you look at the response will be non-sinusoidal. Even if you give a sinusoidal excitation, the current and the induced EMF will be non-sinusoidal. But to characterize a material, you should get sinusoidal flux, right? So this was my first paper. You can see it is in 1983. I joined PhD in July 1980, right? So the idea is very simple. I have something that's jiggly, right? From this, I want a smooth one. What I do is, I just find out what is the difference and remove it, right? That's all. You have something, you want something else, find the difference, make the difference go to zero, right? That's a simple idea. Once we started that, the same thing, if you look at it, it's all almost the same, right? Only thing is it's a slightly different scheme. You remember orange juice, apple juice, right? This again gives you sinusoidal flux, but it's not the same earlier one, right? There is also a lot of advantages here. The amplifier here has to give only small losses, unlike the previous one. Again, you can see the IEEE transactions, right? So the same idea, but different realization, right? Again, this is the same idea. All of you are aware we have three-phase system, right? So all three-phase voltages have to be equal. 230, 230, 230. If you go and measure, it will not be equal, right? Some will be 230, some will be 220, some will be 210. So, but certain applications require that you exactly need 230, 230, 230, all three phases, right? So what do? I know they are unequal. Take the unequal part, put it back so that they become equal, right? That is exactly what is done here. You take the negative sequence here, feed it back, you get a completely balanced set. Again, the idea is, I have something, I want something else, I find the difference, make it zero, right? So that's my PhD. Okay. Then another thing, all of you who are done at least engineering or physics would have done Wheatstone bridge, right? Wheatstone bridge is for inductance, for resistance. If you have inductance or capacitance, Wheatstone bridge will not work, right? You have several other types of bridge. Of that, this is the simplest one. All three arms of resistor and the fourth arm is an unknown element, right? The problem is this bridge cannot be balanced, right? But it's the simplest bridge. Can I do something so that I can use the simplest bridge and measure inductance and capacitance, right? That's the problem. Once you identify the problem, you look for solutions. We can. What you do is, you don't look for balance, you look for two voltages in 90 degrees, right? That's all. You don't, in a Wheatstone bridge, we adjust galvanometer reach zero, right? Here you don't adjust to get zero, you adjust to get 90 degrees between two voltages, right? Once you do that, you get a new, so as I said, Dr. Atmanand retired as a director of National Institute of Ocean Technology in Chennai. That was his PhD. So we started here, we did, again you look at the publication, IEEE transactions, right? Those of you in electrical engineering will know the, at the top level is the IEEE publications, right? To publish in IEEE, your work has to be really, really quality work, right? Otherwise, they won't accept and publish, right? The same thing, you have this 90 degrees, right? where I can apply. Now I have this idea, right? I don't have to have 0, I have to have 90 degrees. So this is the second, this is for testing of two transformers. The same principle, you get 90 degrees, right? Again, you see the two publications. One is a conference publication, the other one is the IEEE transactions and publications. That is PhD of Atmanand. The idea is here that we have a bridge, but we don't look for 0, we look for 90 degrees between two voltages in a bridge, right? So, this is quite, I would say, a deviation from my line of research. Dr. Vinod, of course at the time Mr. Vinod, joined PhD in our department, and he took Professor V.V. Shastri as a guide. And 1 year down the line, Professor V.V. Shastri took voluntary retirement and went to US, right? So he had to find another guide. He came to me, and I asked him, what is your background? He said, machines. I said, I don't work in machines. And Vinod had a very nice word to convince me. He said, sir, I looked around the department, everybody says that you are the best guide. So I will do whatever you ask me to do, right? But take me. I said, no, your expertise is machines. How can I do? Then I said, we will talk to Professor Krishna Vasudevan, who is a machines expert. I will convince him to take you. Professor Krishna Vasudevan said, I already have 2-3 students. So, but I will help. You guide him, I will help, right? So then I told him, okay, we will take a topic in machines, but the topic must be something that I can also contribute, right? So we looked at machines as anything, right? As time goes by, they become bad, right? By wear and tear, or even if you don't use it, insulation slowly, the chemical coating on the wires degrade, and once you switch on, it goes bad, right? So we looked at the falls. Then we found that rotor falls are only of two types. Either the bars are broken or the end ring is broken. Then I told Vinod, okay, we will do this. We will not open the machine. Without opening the machine, we should be able to tell, right? By making measurements on the terminals, that what is wrong with the machine, right? He said, okay, fine. So we started working. Okay, all this. So these are the 3 possible methods. Again, if you are not electrical engineer, you won't understand, doesn't matter. The idea is that I have something like a black box. I should find out what is inside that has gone wrong, right? So then we looked at all the ones. This is the actual rotor, right? So the end ring can break, or the break can be in the right in the middle. So today, of course, I mean, starting from this thing, we have computers. When I started in 80, there were no computers, believe me, right? The only computer that I can access was the IBM 370, for which I have to punch cards, give the card to the machine card reader will read and give me the answer in, again, cards are in a printout, right? Not on your laptop. By the time Vinod joined me, we had IBM PCs in the department, so we could do simulations. So we put the equivalent circuit and simulated. So this is the bar is broken, one rotor bar. So this is one end ring is broken. Then the simulation studies gave us nice results, right? The simulation alone we could publish in an IEEE conference. Then I said, okay, now we will test it, right? Simulation, you can do anything on the computer. Okay. So, the problem came, right? I have to say this the way it happened, right? I was coming to the department on my motorcycle, and I always park in the same place every day, and I saw Vinod was standing there, right? So I went and parked and said, Vinod, why are you standing here? I could see that he was really down, right? He said, sir, I have a problem. I don't think the problem that I have chosen is going to give me PhD. I said, yeah, no, everything is fine. You got results. We have a paper. No, sir, I'll talk to you. Let's go to your room. So I came to the room. He said, sir, now to proceed, to know the fault, I should know the model. Then I'll apply the model and see whether that's a fault or not. Right? But to choose the model, I should know the fault. Right? It's a circular. To know one, you should know the other. I said, I cannot work. I mean, done. Right? Then I told Vinod, no. Yes, if there is a problem, that's good for research. Right? We can find a solution. He said, sir, there is no solution to this. Right? It's written on the wall. I said, no, every problem has a solution. Don't worry. We will find. Right? Then I simply asked him, take a healthy machine model. Don't take a faulty machine model, right? You have a healthy machine, you apply the currents taken by the faulty machine, right? Currents and voltages, and see whether that tells you that the machine has a fault, right? So when we did that, it worked perfectly. You don't need to know which fault. You simply assume that the machine is all right. But you apply the current and voltages taken by the faulty machine onto the healthy machine, it tells, oh, there is a rotor bar broken. There is a, right? And of course, the rest is now history. Vinod was really happy. So that evening, he gave me a 1 kilogram of sweet box. I told him, I cannot eat so much, right? Of course, you have to do, once you have the idea, right, the rest is there. So these are the 4 bars. One has a broken ring, one has one rotor bar broken, one has 2 rotor bars broken, right? And one has just a crack, not broken, right? We could identify without opening the machine. We put that inside, right? And by measuring the currents and voltages and using our algorithm, we can say what is wrong with the machine. So that was PhD, Vinod Thomas. This is where your reading comes in, right? This is an article that came in IEEE Transactions. The 3 papers, 1996, 2002, and 2006, right? This is for sensing rotational angle, 0 to 360 degrees, right? They have a simple capacitive transducer. But the thing is, if you look at the characteristics, they are not really neat, right? All of them are wriggling. Okay? So, what you would like to have? Angle versus output must be straight line, linear. Okay, that's the problem. Okay? So, said, okay, we'll find solution. So, I could find a PhD student at the time. I asked him to make this transducer, right? So, we made the top plate and the bottom plate have 4 quadrants. The middle plate, which rotates as a semicircular plate, and of course the guard ring has to be there for all capacitive transducers. Then we call this as a linear variable differential capacitive transducer. That's a nice name. So you then look at, as I change the central plate, how the angle varies. This is the equation that you get, right? These are the hard work, 99% of hard work that you do. Then you can put it in picture. So these are the 4 capacitance. Now with this, you should get the final output, right? So if you find a function, don't ask me how I got that big equation, right? That was really trial and error, right? We kept on doing a lot of trials, and then finally we found if this is the top equation gives a linear variation with respect to angle. So once you have the solution, of course, you build one, show everything. Again, if you look at IEEE transactions, IEEE proceedings, right? So if your idea is good, and of course, I have stopped here because the rest are all too much of electrical engineering. This is not the only thing Bobby did. He did something more. So that's the work of Professor Bobby George, right? Okay, this comes from the experience, right? As you get older and older, right? You become old, you will invariably go through deterioration in your health, right? In fact, I am 100% sure all of you who are above 40 will need glasses to read, right? That's why in India we call the condition itself, it's not a disease, it's a condition called Chaleswaram, right? Chalis is 40. If you're 40 plus, your eye lens becomes stiff and you need to have correcting glasses to read. No big deal, okay? And similarly, another problem that you will have, especially teachers, I don't know the other teachers, please take care. Many times what happens is we stand and teach, so our veins in the leg will slowly lose their capacity to pump out blood. So there is a test called muscle pump test. Professor Blaschek was my German colleague, German professor. So you put a sensor. The sensor is something like this. One light emitting diode and one photodetector. That's all. Very simple sensor, right? And if you look at what the photosensor will see, it will see the blood vessels, right? And by doing an experiment, you can find out whether your veins are good or not, right? But there is only one catch, right? If for a given volume of blood, delta V, if the person has a dark skin, like an African American or African, right? The signal will be small. On the other hand, if it's a European with very white skin, the signal will be large. So you cannot make any measurement, right? And Professor Blaschek did a nice thing. What he did was, he varied the input intensity. If white skin people are there, he will reduce the input intensity so that you get delta V for the given volume, right? If it's a dark people, he will increase the intensity. So that's actually a feedback loop, okay? And so he had published. So when we saw this, I thought there must be a different way, right? This is how you get a problem, right? There must be a different way. Then I said, okay, let me see what happens to light when it goes in, right? So we said, okay, we have a light that goes in, comes out the detector. This is absolutely not correct, because when the light goes in, I don't know whether I can. Yeah, you can see I have a light here. It's almost collimated beam light. When I put it here, what happens? My entire, this is only small amount of light, right? Small 1 millimeter diameter. But the moment I put it here, I get the entire finger lit up. So the light goes all the way. But we decided, okay, let's not worry about that. Let's assume that the light goes in as a cylinder and comes out at the cylinder. Because if I do that, putting mathematics becomes simpler, right? So all I can do is, now I say I have input light, light goes in cylinder, light comes out. Now I can write mathematical equations for this cylinder very easily. So we did that, right? Now the problem is the attenuation is something like this. For example, if I have my skin, right, with that color is not my skin color. Anyway, assume that it's my skin color, it's orange. So the one in the left is the actual scenario which you cannot model. Again, when you have a problem, you have a solution, right? So we decided, okay, if I give 100 candela at the input, I get 80 candela, right? But that happens all through the cell. I will not do that. I am assuming that the cell is 20% black, 80% white. So if I now give 100 candela, how much I will get? I will get 80 candela. So input and output is the same for both the models. But the second model is a binary model, which is very easy to put it in my program and computer. So that's what we did. We put that in there, got all the equations. Then we, again, I'm not going through this because most of you will not understand. So we got the whole thing, got whole done, and we found nice results that whatever is the intensity, whatever is the color, I am getting the same output. So this was first published in IEEE conference in Singapore. We expanded it to go through the same thing for so this is again IEEE Instrumentation Measurement Technology in 2008. That was PhD of Dr. Ashoka Reddy. I think he's now principal of KITS, Kakatiya Institute of Technology and Science. Right? So this again, as I said, the idea came from the experience. You experience something, you think, okay, oh, this is really not nice, I can do better, right? That's the way you get a problem, okay? And by the way, this we patented it and sold it for 18 lakhs, okay? So you can make money out of research also, okay? So this again, 3:15 is it? When is the 3:15? Okay, I have 15 more minutes to bore you. Okay. So you have sensors. For example, I am sure if you go buy a temperature sensor, right? In the earlier days, you had a mercury thermometer. Today, you won't find a mercury thermometer, right? It's all digital, right? On the digital, the one that senses your body temperature is a simple resistance. Because all of us know, at least in the electrical engineering know, every material has what is known as temperature coefficient, right? As the material's heat increases, its dimension changes, right? We say coefficient of thermal expansion, right? When the dimension changes, its resistance changes, okay? So we have a sensor resistance, which you need to convert to digital. So this is the work that converts the sensor resistance into digital. If you buy a digital thermometer, most probably this is what is inside, right? And of course, this is for a differential sensor, for pressure sensor. The same idea, right? That you have variation in resistance directly converted into digital to read whatever you are measuring, right? And this is the same one, but a different resistor called thermistor. Thermistors are nonlinear temperature sensors. They are excellent in sensitivity, 100 times better than any other temperature sensor. But in life, you never get anything free, right? You get something very good, something will be very bad, right? That will balance. its characteristics is exponentially decaying, right? E power minus x. It's not linear. So what you do is, you once again say, okay, this is the problem I can solve. I can make it linear, right? So we found out a method. We call this as linearizing digital converter. You connect a thermistor, you get a linear reading on the. So this again details. So this is the actual work of Madhu Mohan. So that was PhD Madhu Mohan. Again, I have curtailed it. It's not just those two resistance sensors. He had done a little more analysis, comparison, and so on. Okay. I am sure, again, all of you would have done experiments in your physics lab. Sometimes you vary the resistance using a rheostat, right? So that rheostat is also used even today. If you buy a new car, right? If you press your acceleration or clutch or brake, those signals are taken to an engine control unit called ECU, right? By the way, all new cars, whether you buy the cheapest one or the most expensive one, are all computer controlled, right? Otherwise, you will not get the mileage that the cars are giving, right? So the sensor that you use is something like this, right? There is a resistance, and on that resistance, the wiper moves up and down. Obviously, when something is moving one against other, there will be wear and tear, right? So this is the actual, you can see that aluminum clip that goes into the pedal, right? This is actual sensor taken from, I think, Maruti Baleno, okay, when it got damaged, okay? So that's the problem, right? Can we find a solution? Of course, the solution is quite simple. Why I need to touch? I don't touch, right? I just put an air gap and move up and down, right? But that's not a simple solution, because if I don't touch, I cannot get electrical potential connection, right? It's something like, okay, I have my 230 volts, I put 1 millimeter air gap, nothing will happen to me because I am not touching, right? So nothing will come on the other side, right? Because there is a capacitance when you have an air gap, right? The moment you say I don't touch, you introduce a capacitor. But the rest of the working becomes nice. Now all you have to do is get an output which is independent of this capacitor, right? So this was the idea we got independently, right? The research scholar's name was Supriya. Then I told her, no, go and do literature search. Maybe somebody has done this, okay? To our surprise, Lee and Mayer, they have already thought about this and they have given a solution. And when I looked at the solution, I really laughed. I said, Supriya, don't worry, we have our work cut out. This is so complicated. Why do you want to do all this? We will do simplest way, right? So we did this. If you look at it, it's just 2 op-amps and 1 digital control unit, right? The really simplest form. And we got the output. Again, I am not explaining. Okay, this is all whole thing. Yeah. Where is it? Yeah. So we got an output that is linearly varying with the movement, right? So from the manufacturer's 1,000 operations, after 1,000 operations, they normally go down. They do a lot of things to make it 10,000. And once we gave this, now it is 1,000,000 operations. Only after 1,000,000 operations, it fails. Because anything that moves will also fail, right? Whether you touch or you don't touch, it doesn't matter. But now today you can get a resistive sensor, resistive displacement sensor that has 1 million operations as life cycle. Right? And you can look at the publication again, IIEEE transactions on instrumentation measurement in 2015. Of course, once you have the idea, you go and expand. We slightly change the circuit so that you get a better performance, right? Orange juice, grape juice, same thing here, but not so crude, but slightly, you get a better this thing. Again, I will not explain the, so you get the output proportional to small x, the displacement, okay? So this is a quotation from, I've become old. I think it's from Socrates, right? Discovery happens when a prepared mind meets a challenge, right? So there are two important words there. Prepared mind, challenge, right? If you should have a prepared mind, that's the first one, right? So how to prepare a mind? As I said, read as many articles as possible, okay? So if you have chosen an area, or even to choose an area, go and read articles, right? As I said, maybe the first 1,000 articles you won't understand. Does not matter, right? Continue till you come to something that you like, that you understand. Many times students ask me, how do I know I like it? I said, if you like it, you will understand, right? Or the other way around, if you understand, you understood because you liked it, right? Then, once you start doing, never give up. There will be bottlenecks, right? Like Vinod ji coming and crying, saying that my PhD is down the drain. There is a problem that cannot be solved. Please, any problem can be solved, right? So that's the attitude. You should never give up. Okay, thank you. Normally in my class, I always say, teaching learning happens when questions are asked, right? So questions must be asked, and in my class, regular class, right, there is an unwritten rule. If students don't ask questions, I start asking them questions, right? So students always ask me questions. They don't want me to ask them questions.
Thank you, sir, for making us a part of an engineer's odyssey. And we can see all the adventures you've had right from writing a very reckless letter to ISRO. I can see the kind of passion you had towards your research at that time once that you had found your challenge, because you had prepared your mind and you had met the challenge. That is why you were able to write that kind of a letter to ISRO and sustain yourself in this particular field, and now an emeritus professor at IIT Madras. So this particular odyssey that sir took us through had helped us in many ways. Like sir said, this is the time for questions that you should be asking. It's okay if you do not ask questions about electrical engineering. I know that there are some active participants from the electrical engineering faculty here. Other students can also ask questions. So one thing I should tell you was, I was looking at the consistency of your publications in IEEE journals. You made sure that all your scholars had to do that kind of work and publish. So I hope a lot of supervisors also encourage our scholars to do publications in top-notch journals. Yes.
First of all, if you go down to a journal which is not good, you are degrading yourself. That's very important. I would never degrade myself. I always think I am great, right? If you think, you yourself think you are not great, you will never become great. It may not be that you are not great, right? I know I am not really that great. But if I have that attitude that I am not great, that's actually a very bad thing. It will keep you going down and down and down, right? You always aim high, right? And the one thing I have found, if you go to very good journals, right, the feedback that you get is excellent. So even if you are going, it's not good enough, you think it's not good enough, put it to a top journal in your field, right? The feedback that you get is really invaluable, finally.
The reviewers' comments, you mean,
Yes.
sir? The reviewers' comments can help us, grow as researchers and as better paper writers in future. Yes. So can we have some questions for sir? So we also have a big online group. We will also
Okay.
check for questions from there. Can you pass on that mic, Ganesh, to him?
Hello, sir. Good evening. Sir, everybody will ask only what is the application of your research? Like supervisors, everybody will ask only, right? Whatever
Yeah.
our research, what is the application? So here you give some example, right? The fruit juice experimentation. It is only the basement of studies, right? It is only whatever the final result will give some studies.
No, PhD, as I said, is an idea and providing new results.
Yeah,
Right?
shall we publish the papers basement on studies also, right?
You can.
Yeah.
That depends upon the area, right? For example, if your area is humanities, right? I know one of my colleague with whom I have very close interaction. She works in cinema studies, right? Studies on how directors have directed, how actors have acted, I sometimes really it mind boggles that so much can be looked into in a cinema, right? We all go there, enjoy 2.5 hours or 3 hours and come back, right?
Yes, sir,
We don't look at the nuances. There are nuances in every work, every field.
Yeah, actually, I am working in polymers. Actually, my topic is only studies on polymers, particularly. So there is, but even somebody will ask, what is the application of your research, or what is the novelty? So
Yeah.
we are doing on studies, right? So
Yes.
why we want to give the application? So we can choose this type of topic also, right?
See,
Studies only.
when you do a research, there will always be criticisms, right? For all of you, people will say, oh, your work is done nothing, right? That simply means the person has not understood your work, right? If you think that you have come up with something new, that's enough, right? And if that is proven in your field, your peers, right? Maybe a professor sitting in America looking at your paper and says, okay, this can be published in IEEE. That's the thing that you need, right? Not somebody else saying that, oh, what is the use of this, right? Okay, so as I said, fruit research, what do you get? Nothing. You get effect of sun rays on orange juice.
It's only studies.
Yeah, that's fine.
Thank you. Thank you.
Maybe during the study, you may find a new polymer, right? You keep your eyes open. Okay.
Okay. So if there are no further questions, we will close the session here, sir.
Yes,
Thank you
thank
for
you.
your patience in answering all the questions. It was an excellent session. The story of reading 1,000 research articles from all the IEEE journals, it's definitely an odyssey.